In this video, I'm going to walk through a required practical from the rates of reaction topic. There are two required practicals in this topic, and this video will focus on one of them. We're going to calculate the rate of reaction by measuring the volume of gas produced in a reaction. The reaction in this practical is between magnesium and hydrochloric acid. This produces magnesium chloride and hydrogen gas. We're going to do this reaction first of all with 0.8 molar hydrochloric acid, and we'll measure the volume of hydrogen produced every 10 seconds. We'll then repeat this reaction, but this time with a more concentrated acid at 1.6 moles per decimeter cubed, and again we'll measure the volume of hydrogen that's produced every 10 seconds. This is the apparatus needed for this reaction. So we've got a conical flask which contains the hydrochloric acid and the magnesium that's going to react. We've also got a bung and a delivery tube. Now these pieces of equipment are so that when the hydrogen gas is produced in here, it doesn't get lost into the air, it goes into this delivery tube. We've then got a trough of water and the measuring cylinder, and that's where the hydrogen gas is going to be collected, and that's held up by a clamp. We're going to record our results on a table like this. We need a column for the time elapsed in seconds, and in the next two columns we're going to record the volume of gas produced. The first of these two is for the reaction involving the 0.8 molar hydrochloric acid, and the final column is for the reaction involving the 1.6 molar hydrochloric acid. Now let's go and see how this practical is carried out in the lab. Here is all the equipment. From the left we have a conical flask and delivery tube, and I've already filled the conical flask with 50 centimeters cubed hydrochloric acid. Then we have the magnesium strips, and you'll need two of these, both 3 centimeters in length. Then we have our 100 milliliter measuring cylinder, stopwatch, water trough and clamp stand to hold the measuring cylinder in a moment. First of all, you need to completely fill the measuring cylinder with water, so that there are no air bubbles whatsoever. The way to do this is to lower the measuring cylinder into the water bottom first, then slowly make it more and more horizontal by tilting the top downwards as it fills with water. If you make sure the opening is the last part to enter the water, it should be air bubble free. You then need to turn it upside down and clamp it vertically whilst keeping the opening in the water. Make sure you clamp it so that the graduations and numbers are in a position that you can read easily later on. Next, you need to take the end of the delivery tube and place it into the measuring cylinder. At this point, I'm going to start the reaction and measure the gas given off. Before you do this, make sure you have your results table ready with a pen and stopwatch. Place the magnesium strip into the conical flask, close the bung, and start the timer as swiftly and safely as possible. As soon as 10 seconds shows on the timer, read the volume of gas collected in the measuring cylinder. Now if the gas is produced really slowly and you have a measuring cylinder like mine that doesn't have graduations until the 10 centimeter cubed mark, you're going to have to estimate the first few readings. A way to avoid this issue is by using a gas syringe to measure the volume of gas given off. Every 10 seconds, read the volume of gas in the measuring cylinder and keep going until no more gas is produced. I found that I had to extend my results table onto a second piece of paper. You might notice my head bobbing down to read the measuring cylinder. That's because you absolutely have to make your eyes level with the waterline to take an accurate reading. If your eyes are above or below it, then you're going to read it incorrectly. Here's a look at the end of the reaction. As you can see, there's no magnesium left to react and no fizzing, which means no more gas is being produced. You can also see no more gas is filling this measuring cylinder. Time to start the second reaction. I've already filled the conical flask with 1.6 molar hydrochloric acid. Now I need to set up my apparatus again, refilling the measuring cylinder with water and no air bubbles, and feeding the delivery tube into the bottom. Again, try to be as quick and safe as possible when putting the magnesium into the conical flask, replacing the bung and starting the stopwatch. As before, take a reading every 10 seconds. This part of the video hasn't been sped up. That is the rate that those bubbles of hydrogen gas were being produced. You can see the bubbles of hydrogen gas are produced much more rapidly this time around, and the reaction is over quite quickly. Now I'm going to speed the video up to the end of the reaction. Let's have a look at these results more closely. So here is my results table in full. You can see it took much longer for the reaction to finish with the less concentrated acid. Now I'm just going to alter this table slightly and get rid of the middle readings for now, so we can make some comparisons. The reaction with the acid of higher concentration finished much sooner than the reaction with the acid of lower concentration. You can see the high concentration acid reaction was over at 40 seconds, but the low concentration reaction wasn't over until 220 seconds. Notice that the amount of hydrogen produced is roughly the same, 58 or 59 centimetres cubed. That's because the size of the magnesium strip was 3 centimetres for both reactions, so no more hydrogen can be produced, but it can just be produced faster. The reason for the slight difference may be due to a very small difference in the size of the magnesium, or it could be due to some gas escaping the conical flask before I replaced the bung. From these results, you can calculate the mean rate of reaction. This is done by dividing the time taken for the reaction to happen by the quantity of hydrogen produced. So here's our results table again. For the reaction involving the 0.8 molar hydrochloric acid, 58 centimetres cubed of hydrogen was produced in 220 seconds. So the mean rate of reaction was 0.26 centimetres cubed per second. This means that every second, 0.26 centimetres cubed of hydrogen was produced. For the reaction involving the 1.6 molar hydrochloric acid, 59 centimetres cubed of hydrogen was produced in 40 seconds. So the mean rate of reaction was 1.48 centimetres cubed per second. This means that every second, 1.48 centimetres cubed of hydrogen was produced. What we can take from this is that an increased concentration of hydrochloric acid increases the rate of reaction. Here I have put my results onto a graph. Now this is done on Excel, so I wasn't able to draw the nice sciencey line of best fit, and you may notice that the points are actually joined up one by one, and you should not do this. If you ever draw a graph like this on paper, you should use a pencil and draw a curved line of best fit freehand. But let's work with what we have here. We have the reaction involving the 0.8 molar hydrochloric acid in this mustard colour, and we have the reaction involving the 1.6 molar hydrochloric acid in this teal colour. We have the volume of gas produced on the y-axis and the time in seconds on the x-axis. In graphs like this, faster reactions have steeper gradients, so we can see that this is the faster reaction. In addition, in faster reactions, the line becomes horizontal sooner. This is when all the gas has been produced, and so every reading afterwards will just be the same because no more gas is being given off. Conversely, slower reactions will have more gentle slopes, and the line becomes horizontal later as the reaction takes longer to produce all the gas. The next bit of analysis of this graph is a higher tier part of the AQA specification. What you need to be able to do is measure the rate of reaction at a specific time. So I've arbitrarily chosen 15 seconds to try and find the rate for both reactions. The way you find a rate of reaction at a point in time is by finding the gradient at that point. So we need to find the gradient here for the faster reaction and here for the slower reaction. So let's start with the slower reaction. To find the gradient at this exact point, you need to draw a tangent line as best you can. Then you need to draw a triangle and try and make this as large as reasonable, as you'll get more accurate results with a larger triangle. Choose to make your triangle at points where reading off the numbers is going to be easier for you. And what I mean by that, find places where the tangent lands where the grid lines cross. So I've chosen this point because the tangent lands on an intersection, so it's going to be really easy to read the value of this point on the x and the y-axis. The same goes for here. I saw that the tangent ran through the origin of the graph, so this is a really easy place for me to read the points of this coordinate. Now, this vertical line is called the rise, and the horizontal line is called the tread, and the gradient is worked out by dividing the rise by the tread. So to do that, we need to know the lengths of these two lines, which is where reading the values comes in. Looking at the rise first, reading from the bottom of that line, we're going to call that y1, and it's at 0 centimeters cubed. Then the top of the rise is y2, and that's at 28 centimeters cubed. Now the tread starts at x1, and that's at 0 seconds, and it goes to x2, which is at 140 seconds. So as I've said, the rate is equal to the gradient of the tangent, which is calculated by rise over tread. The rise is y2 minus y1, and the tread is x2 minus x1. Plug those numbers in, and we get 28 minus 0 divided by 140 minus 0, which is just 28 divided by 140. This gives us a rate of 0.2 centimeters cubed per second. Now we're going to compare that rate to the rate of the faster reaction when it was also at 15 seconds. So again, we need to draw a tangent at this point in the graph. Draw a large triangle so that we can calculate the rise and the tread. In my triangle, y1 is 12 and y2 is 56. x1 is 5 and x2 is 25. The rate at this specific time is equal to the gradient of the tangent, which is rise over tread. This is calculated by y2 minus y1 over x2 minus x1. Plug the numbers in and we get 56 minus 12 divided by 25 minus 5, which ends up being 44 divided by 20, which equals 2.2 centimeters cubed per second. I hope this video was clear and useful. I have plenty more required practical videos on my channel, so feel free to watch those.